action. Ba-da-dun-dun-dun, let's make life easier dun-dun-dun-dun, for everybody now. Okay, so what we have looked at before for a charged disk is an electric field. What we're going to look at now is an electric potential for a continuous, not a ring, but a disk here. And we're also going to get back the electric field from doing this. So how do we go about setting this up here? Well, when we're looking for potentials, we're looking for voltages, right? And voltages are scalars. So what we're really going to do here is we're going to say, hey, look, I know what the voltage due to a ring of charge is. We saw it in our previous video. If you haven't checked it out, you need it for this one. So I know that the voltage due to a ring is simply KQ, where the charge is on that ring, whatever it is, divided by, and then this is kind of weird, it's the square root of r squared plus z squared. So r squared plus z squared to the 1/2 power. That's what the voltage is for a ring. Now I know, based off of a previous video we've done for the electric fields due to a continuous disk, that a number of rings stacked together will get us a disk. You know, right here I've got a green ring, but I think, you know, if I put another red ring around it, and if I put a pink ring around that, and then I put a blue ring around it, if I keep stacking these rings up, I'm going to get a disk eventually, okay? Now what we're going to do here is we're going to set an infinite number of rings with an infinitesimally thin distance over and over and over again to build up our ring here. And since voltages are scalars, if I simply add up or sum all of the voltages of these individual rings that I have, I'm going to get the total voltage here, which will be the voltage of the entire continuous disk. So what we're setting to do here is to then simply say, look, if I find K, which is Coulomb's constant, 1/4 pi epsilon naught, multiplied by the charge of an individual ring divided by, and this is a little bit different, not big R squared, but little r squared, because that's an individual ring's position, plus z squared to the 1/2. If I'm able to just sum all of these up, and that's the weirdest summation ever, if I'm able to sum all of those up together, then I'll be set. If I can just sum all of the rings, I'll be good. Well, first thing we can recognize is that this k is a constant here, so I can actually pull it out of the summation, and then we actually start getting a little bit of a headache in this case. You know, when we did the ring, we didn't have to take an integral because it was just a ring. But in this case, these r values are changing as we move out. You know, if we take a zoom into our picture here, that r value right now is just for the green ring, but when I go out to the next ring, it's going to be just a little bit further, and then a little further, and then a little further, and a little further. And because all these r values are infinitesimal in their length, I'm going to technically need an integral here. So what I really want to do is want to say, look, if I want to find the total voltage here, I'm going to have to take k multiplied by some integral here of all of the individual charges that I have. So all the individual charges over all of the ring positions as well. And we know, like, this doesn't look very nice because, one, what am I integrating over? You know, I don't have a dq here, which we don't even want to use anyways. I don't have a dr. Where is it? What am I actually integrating over? This isn't very helpful. So how can we break this down? Well, one of the things we need to remember is that this charged disk has a continuous charge distribution. So if it has some total charge here, like plus q, across the entirety of the disk, this disk has a surface area density. Okay, it's got a density on this disk. So what we can say here is that the entirety of the disk is equivalent to some surface area density, sigma, multiplied by the area of the disk itself, which we could just say here that this is sigma times, well, what's the area of a disk? Pi r squared, where this big R is the entire radial distance of the disk. Okay, that's our total charge that exists. Now, if we wanted to just say, okay, what is the amount of charge here in our ring? You know, we've got this green ring right here. It has some charge on it, Qi, where that's like the individual charge on each of the rings. So what is it just on one ring then? Well, we can actually find this out too. You know, if we think about it, we could say that, the charge on an individual ring is equal to the surface area density multiplied by the area of an individual ring. And you know what the area of an individual ring is. In our prior video, when we were looking at the charged disks, we saw that this is like a circle that we rolled out flat. So that's 2 pi r right there. That's the circumference of the circle. Just we've unrolled it. That's the length. And then this circle, if it has some thickness to it, that thickness is infinitesimal. That's some dr right there. So we know that this circle, or this donut, this ring rather, has some area here, dA, which is equivalent to 2 pi r dr. So we can say that Qi here is going to be equal to sigma times 2 pi r dr. And what's going to be really cool is I can actually get rid of this sigma. I can keep it around if I wanted to. There's no problem there. But I can actually get rid of it as well. I know what sigma is if I know what the charge total is. I know sigma is just going to be equal to the total charge bloop, divided by pi big R squared. So I can take this value and plug it here. And what this will allow me to do, I could have left that as sigma. I really could have, but I'm going to change it. What this will allow me to do now is, in taking this integral, I can say that this voltage is going to equal K times the integral of Qi, which is going to be Qt over pi r squared times 2 pi r dr, because that's everything Qi is. So times 2 pi r dr, that's all of Qi. And then I can divide this by this radical in the denominator, this r squared plus z squared to the 1/2 power. And this actually looks kind of nice, because now what I'm basically saying is, look, I'm taking all of the rings and I'm adding them up across the distance of those rings. So I can identify here some constants. To identify constants, Qt is the total charge, that's the constant. Pi is a constant. R squared, that's the R of the entire ring, so that's a constant. This pi here is a constant, so I'm going to whip it outside too. Actually, I don't have to. I can see that these pi's are going to force each other away. And while this 2 is a constant, I'm going to keep it inside because I can see into the future, and maybe you can too. So if I pull all my constants out, what I have now is this. I have k, which is actually 1 over 4 pi epsilon naught, we'll come back to that, times qt over r squared, times the integral of 2r dr over r squared plus z squared to the 1/2 power. And what am I integrating here? Well, I'm integrating from the center of the ring, 0, out to the edge of the ring, because I'm integrating these radial distance here, so the edge of the ring is big R. So that's what I'm integrating to. Now, if you're looking at this, maybe you've seen this integral before. If you watched our prior video for the electric field due to a continuous disk, you have seen an integral very much like this. What you'll notice is that I'm going to use a u substitution. U is going to equal r squared plus z squared here. That means du is going to equal, taking the derivative of this, 2r dr. Remember, z is a constant, so the derivative of a constant is nothing, it's 0. So we just get 2r dr, which, hey look, there's my 2r dr. Helps us out. So now, pull my constants down, integrate 0 to r. Technically, you could change these bounds if you like to when you do your u subs. I just like to undo the u's afterwards. It's however you float your boat. Du over u to the 1/2 power. Looking at the integral here, this is going to be the same idea as u to the negative 1/2 power du. That integration is fairly straightforward. You add 1 to the exponent, so we're going to get u to the positive 1/2 power, and then we're going to divide by that exponent. So dividing by 1/2 is like multiplying by 2. So down here, we get our constants, k qt over r squared. And then for the integral, we're going to get 2u to the 1/2 power. And this is going from r to 0, which means if I expand that u, this is what I'm talking about, you get k qt over r squared, and then my expansion of u, it's going to be 2 multiplied by the r squared plus, r squared plus z squared to the 1/2 power, and this is bounded from r to 0. I can pull this 2 to the outside, it's a constant, and then whenever I'm putting in my values of r and 0, they go in for r right here, because that was the bounded term we were going across. So when I do this, I'm going to get 2k qt over r squared multiplied by, and on the inside here, I'm going to have r squared plus z squared to the 1/2 power minus, and then this is just going to be, when I put the 0 in for r squared, it's going to be nothing, so I'm going to get z squared to the 1/2 power, so just minus z. Okay? That right there will give us the voltage. That will give us the voltage due to an electric field at a position away from our charged disk. Okay, so that is actually what I'm looking for right here. If you wanted to, you could clean this up. If we kind of zoom in on this, you might recognize some neat things we can do here. Maybe you're rewriting k as 1 over 4 pi epsilon naught, which means that you could write this as 2 qt over 4 pi eps naught r squared, and then here's the, all of this term. What you could recognize here is that not only do the 2's go away, well, the 2 and the 4, they kind of divide out, but you recognize you have a pi r squared and q of t. That's just the total charge over an area, the area of the disk. That is your charge density. So if you wanted to, you could just write this as sigma over 2 epsilon naught, and then you could multiply by the quantity r squared plus z squared to the 1/2 minus z. That is this just carried down. So that will also be an answer. I said before you could carry that sigma through, but we just kept the q's and the pi r squared. Look, I can get the sigma back if I wanted to. The other really cool thing with this you can do is if you liked the voltage method, if you found finding the voltage at a point in space easier than thinking about the charge distribution for an electric field, you can actually get the electric field from this. If you recall, we know that an electric field is oh, that looks terrible. Why does that look so bad? We know that the electric field is equal to the negative derivative of the voltage with respect to some radial distance. Okay, so sometimes you'll see this written as dr. In our setup though, our radial distance is a distance z away from the actual charged disk. So instead of writing dr here, I'm going to write dz because that's our radial distance. So if I was setting up this derivative, this is going to be negative of the derivative of, and then this entire term up here, sigma over 2 eps naught times r squared plus z squared to the 1/2 minus z over dz. So what this means here is that I'm just trying to take the derivative of this with respect to z. And this is actually a pretty easy derivative to take. If we kind of look at it, the only thing we really have here is we have a derivative of this and z, which the derivative of z is a very straightforward integral or derivative. It's just going to be 1. This here, the r squared plus z squared to the 1/2, is a little bit more complicated. We have to implement a chain rule. But if we do this, we're going to get our negative, which we haven't forgotten about. Negative, let's just float it there for a while. Here's our constants, sigma over 2 epsilon naught. And then if we take the derivative of this first term here, I need to take the exponent in front, so there's a 1/2, and then multiply by the quantity again, r squared plus z squared, and then to the negative 1/2 because I've subtracted 1 from that exponent, and then I need to multiply by the derivative of the interior with respect to z, which is going to be 2z, minus, and then just derivative of z is 1. Okay. What can I do from here? Well, I can very quickly see that the 1/2 and the 2 are gonna work each other away, and because I've got this negative exponent, that's gonna go into the denominator. So I'm gonna have negative of this big thing, sigma over 2 eps naught, and then this is gonna be multiplied by z over r squared plus z squared to the 1/2 minus 1. And then a neat little math trick is if you have a negative on the outside of here, I'm going to take a look at this and I'm going to flip these positions. I'm distributing this negative throughout this, but what will happen here is that this 1 will be positive and the front term will become negative. So the way it will look finally is it will equal, so my electric field will equal sigma over 2 epsilon naught multiplied by the quantity 1 minus z over the quantity r squared plus z squared to the 1/2. And maybe you liked taking that derivative a little bit more than what we did previously, because if we go back to that old solution, look, it's the same thing. This was our circular disk that we integrated for an electric field earlier. It kind of looks similar, but you might notice that, you know, the calculus is all there. But we get the same answer in the end. It's that epsilon, or it's that sigma over 2 eps naught, 1 minus z over the quantity r squared plus z squared to the 1/2. Now when we do it for electric potentials, we got our potential solved, and then whenever we come down to the end and take the derivative of it, we get the exact same answer for our electric field. So however you like to solve that, it's really up to you on the test, or whenever you're doing this. Some people like to get potentials, then take the derivative of them. Some people just like to get them straight up. But we get back the same thing once again, which is a pretty cool idea. Yeah, so that's it for the potentials for either a curved arc or a curved ring, which we saw in our prior video. And then this was how we get the potential for a curved disk. Right up here, this 2k qt over r squared times the quantity, or sigma over 2 epsilon naught times this quantity. However you want to write that. Either way, this is all finished. I hope you enjoyed those derivations. I hope those help you out. You should know how to do all 6 of the derivations that we've done for electric fields and potentials. There's really 5. But you should know how to do those front and back for the AP test. One of those will come up every few years, and it's just something that if you know how to do it, that's 15 free points you're getting right there. But until next time, adios, and y'all take it easy.